We're talking about theoretical and experimental probability. So again, the idea of probability is it's an event out of a total. That's what we discussed yesterday. You have two different formats of your probability. Theoretical probability is the idea of this is what should happen. So when you flip a coin, how often do you think you should land on heads? Half the time, right? Now, how many of you have ever been like, okay, I'm going to flip a coin, and several times you always just seem to land on one side? I always land on heads, or I'm always landing on tails. So in theory, we should land on heads half the time. But when you start actually flipping the coin, it doesn't always come out to that way, which is what is the difference between theoretical and experimental. Theoretically, you should land on it half the time. Experimentally, maybe today you flipped it 10 times and you landed on heads 8. Tomorrow you flip another 10 times, maybe land on heads 6. Okay, so it's always going to be different. Experimental probability will always change. So go ahead and write this up at the top. For theoretical probability, we call it the probability based on the specific item, and that there is no action. You are not doing anything. When I say the probability of flipping a coin, you don't have to actually flip the coin. You just know, hey, there's 2 outcomes on the coin. Half the time there's heads and half the time there's going to be tails. So we label this the probability of what should happen. What should happen. So again, in theory, probability of landing on heads, that's what we label for probability. It's P and then parentheses an event. It's probability of heads. That's going to equal 1/2. That's in theory. And again, theoretical probability, you are not performing anything. You are literally being told, here's the action here, or here's the experiment or activity. Before you do anything, what's the prediction? Experimental probability is different. It's based on an experiment, not the item itself. So yeah, you've got a coin. You know that you should land on heads half the time. But for experimental probability, your probability is actually based on an experiment, meaning that there has to be action. You have to actually be doing something. You have to actively be flipping a coin or actively spinning a spinner. An action has to occur for there to be experimental probability. So in cases like this, we call it the probability of what actually happens. So if you've got tests coming up and you study, what should happen? You should pass. How many of you have ever come across a test where you studied, and you studied hard, and you didn't pass? It happens. It happens to the best of us. In fact, it happened to a good amount of you for your final exam. Y'all worked really, really hard. We practiced and practiced and practiced in class, and yet most people didn't pass that final exam. Okay? The fact that you studied, in theory, you should have done well. But when we actually took the test or that final exam, the results were different. So your experimental probability is going to have different results than your theoretical probability until a certain thing happens. We'll talk about that in a second. So again, for experimental probability, there has to be action, which means I have to have trials. Who remembers again, what is trials? Jimmy? Okay, so when you perform that experiment over and over and over again, you have to have more than one trial for there to technically be the experiment. So you're going to flip the coin, we'll say 30 trials, right? We're going to flip it 30 times. And maybe it lands on heads 8 times, and it lands on tails 22 times. So now the probability of heads is no longer 1/2. The probability of heads is 8 out of 30, which again, we always need to simplify. That's 4 out of 15. So it's smaller than 1/2. But again, in theory, it should have happened half the time. But in reality, when we performed a small amount of trials, we got a different result. Now, if I flip the coin 30 times and Ramla flips the coin 30 times, are we going to have the exact same results? No. So experimental probability is always changing. Theoretical probability does not change. The theoretical probability of landing on heads will always be 1/2. But the experimental probability of landing on heads is always going to be different depending on, who did this, who performed the experiment, how many trials did they perform it for, and the fact that you're doing it a different amount of times each time. So maybe today I flip the coin 30 times, and then tomorrow I flip the coin 30 times. Those results are still not going to be the same. Okay? All right. Let's go ahead and look down here. The graph off to the right is going to show an experiment in which a spinner of 3 equal sections has been spun 60 times. 60 represents the number of trials. Number of trials, 60 times. We want to know what is the theoretical probability of spinning red, and then what is the experimental probability of spinning red. So again, theoretical probability is based on the item. So theoretical for here is based on the actual spinner. Experimental probability is based on the results or the action of spinning the spinner. So this table, this graph, is your experiment. We're not going to use this when doing theoretical probability. When we're doing the theoretical probability, we have to focus on what the spinner would look like. So it says here that it's a 3-section spinner. So I should draw a circle with how many sections? 3. 3 equal sections. And it says here the colors are green, blue, and red. All right? Here's blue. Here's green. Here's red. So based off of my spinner, because again, theoretical probability is based off the spinner. What is the probability that the spinner would land on red? 1/3. Right? There's 1 red out of 3 sections. That's approximately 33%. 1/3. Now, my experimental probability. The experimental probability is based off of this, my actual experiment, the table that I see over here. So based off of the table, the probability of spinning a red means how many times did I land on red out of how many total trials. So looking at the table, how often did I land on red? 24 times. How many trials were there again? 60. You could have either gone back to the problem where it said we did it 60 times, or if they didn't put this here, how else could we figure out the total number of trials? Add them all together, right? 21, 15, and 24 added together will give you 60. Okay, so this is going to be 24 out of 60. This can be simplified. If you don't remember how it can be simplified, you can always plug it into your calculator, but they are both divisible by 12. That's the largest that they're divisible by, and that would give you 2/5. And 2/5 is 40%. Now it says to compare them. It says, hey, compare your experimental with the theoretical. So we're comparing 40% to 33%. Which one's bigger? 40%, right? Your experimental probability of 40% is greater than your theoretical probability of 33%. Now, to get these two to be close, here's a little footnote that you want to make. If you want your experimental probability to be equal to your theoretical probability, if you want your experimental probability to be close or equal to your theoretical probability, you need a large number of trials. The more times you perform the experiment, the closer the results are to each other. The more times you perform the experiment, the closer the results are to each other. And I'll show you guys that tomorrow with a coin simulator online and a dice simulator online. Yes. 2 out of 5 is 40%. 2 divided by 5 times 100, that gives you 40. Okay? Yes. When I added 21, 15, and 24 together, it gives you 60. Or if you just read the problem, it says 60 times. Yeah. Any other questions? All right, let's go on to the next page then. You got it? All right. Page 23. The graph shows the results of an experiment in which a number cube is rolled 50 times. So how many trials? 50. We want the theoretical probability and the experimental probability. The theoretical probability, is that based off this table? No. Theoretical, it's based off of the item. What item are we, what's our activity? A cube, a die, right? So again, this is theoretical. It's not off the table. It's off of an actual die. So if I were to draw a little number cube here, maybe I've got a 3 in the front, a 2 off on the side, 4 in the top. Okay, that's my number cube, my die. It's based off of the actual die. I want the theoretical probability of landing on the 4. How many 4s exist on a die? 1 out of 6. So it's 1 out of 6 for our probability, our theoretical probability. Now, if I sit there and roll the die 6 times, is it going to land on a 4 one time? Maybe. Maybe it doesn't land on it at all. Maybe it lands on 4 multiple times. This is, again, just kind of like a prediction. It's an estimate of how often it should happen. But the experimental probability is what actually did happen. So experimental probability is going to be based off of that data, that graph that we have here. So how many times did we actually land on the value 4? So let's take a look. Here's the 4. The line goes up halfway between the 8 and the line above it, which is that 10. So what's halfway between 8 and 10? 9. So it's going to be 9 times out of how many total trials again? 50. Again, if they didn't tell you 50, you could always just add these values together. What are these numbers down here? 1, 2, 3, 4, 5, 6. The number you landed on, right? So this says, hey, we landed on a 1 how many times? No, what's 6? We landed on a 1 6 times. It's counting. Each line represents a 2. So this is 0, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay? So we landed on a 1 6 times. We landed on a 2 12 times. Landed on a 3 11 times, right? It's between the 10 and the 12, so it's 11 times. Landed on the 4 9. Landed on a 5 6 times. Landed on a 6 6 times. So that's just indicating how many times it landed out of 50 times. So 9 out of 50, which in this case would be 18%. Again, if you take 9 divided by 50 and multiply by 100, that's 18%. Okay? Now, 1/6 is roughly 17%. So are they close? Yeah, they're pretty close. But in this case, which one's larger? The 18%, right? Our experimental probability of 18% is going to be greater than our theoretical probability of about 17%. It's 16.6 repeated percent. Okay? They're close, but they're not equal. So if we performed even more trials, it might become even closer. Yeah. 1 out of 6 is because there's one value of a 4 on a number cube. So if you take a die, the 4 only occurs one time on this die, right? Right here. That's a 4 out of 6 numbers on the die. So it's 1/6 is the probability in theory. Remember, theoretical probability is just the item, not me flipping it. I haven't done anything. There's no action. I'm just holding it. The experimental means I've actually had to flip the die over and over and over again for 50 trials and calculated how many times I landed on each of them. And in this case, for my experiment, I landed on a 4 9 times out of the 50 total times that I rolled the die. That's the experiment. Stephania? 9 divided by 50 multiplied by 100 will give you 18. Yes? 1 divided by 6 multiplied by 100 will give you 16.6 repeated, which is roughly 17%. Is there a what? What do you mean right or wrong answer? Like so these are, again, this is like what you're striving for. So it's kind of like a goal. You want to get to 1/6 as your probability. The experiment is you actively trying to get there. And again, like I said before, if you want to get there, you have to perform your experiment a large number of trials, which I'm going to show you the reason why for that tomorrow with a simulation. So this is, it's like theoretical is the correct answer. Experimental is you working your way to the correct answer. Okay? All right. Down here at the bottom, we're going to try a little experiment. So we're going to roll 2 dice, and we're going to make notes of the sum that we get from each roll. Okay? So first we need to make the chart of all our possible outcomes. So this is listing all possible outcomes. So we've got a red die. Oh, I don't have my red die anymore. Really? Well, I've got my green. Okay, well, I'm going to use a double die instead. Just ignore the inside one. We're going to focus on the outside one. So we'll have red and we'll have green. So they're 2 separate die. Now, when I'm making my list of what they can land on, the first die, the red die, can land on a 1, and the second die could also land on a 1, right? That's a possibility. But I could land on a 1 and then land on a 2. Or I could land on a 1 and then land on a 3. I could land on a 1 and then land on a 4. I could land on a 1, land on a 5. I could land on a 1, land on a 6. So I could keep the red staying as a 1 and just the green is alternating. So for here, when I'm listing out my possible outcomes, a 1 1, a 1, 2, a 1, 3, a 1, 4, 1, 5, and 1, 6 are 6 different ways that I could have red landing on a 1 and green landing on something else. Does that make sense to you guys? Now, the sum, what does sum mean? Add them together. So what's 1 plus 1? 2. 1 plus 2. 1 plus 3. 1 plus 4. 1 plus 5. 1 plus 6. There you go. Now, does a red die have to land on a 1? What else could it land on? A 2, a 3, all that, right? So if it lands on a 2, the green could still land on a 1. So we could have a 2, 1, and we could have a 2, 2, a 2, 3, 2, 4, 2, 5, 2, 6. And then those sums, when we add it together, that would be a sum of 3, 4, 5, 6, 7, and 8. Oh, but the red could also land on a 3. So we could get a 3, 1, a 3, 2, a 3, 3, a 3, 4, 3, 5, and 3, 6, which would give us sums of 4, 5, 6, 7, 8, and 9. Red could also land on 4. So we could have a 4, 1, a 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6 for sums of 5, 6, 7, 8, 9, and 10. We could land on a red 5. So 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. And filling in our respective sums. And then the last value red could land on would be a 6, right? So 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6 for values of 7, 8, 9, 10, 11, and 12 for the sums. So this is the table of all possible ways we could roll these 2 separate dice and land on these different combinations. When we come back from lunch, we will go ahead and finish up these notes. So all I've done here, I've highlighted every way that I can get a sum of an 8 or larger. So an 8, a 9, a 10, an 11, a 12. All of those sums are part of the probability that we're looking for. And again, this is theoretically. So have we done an experiment yet? Have I actually flipped any coins or any dice? No, haven't flipped anything yet. So we've just made our table. There's 36 total outcomes. How many outcomes am I able to achieve in 8 or higher? 15, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 ways that I am able to get an 8 or higher for the sum. So let's turn back to this slide. Again, the theoretical probability of a sum that is greater than or equal to 8. We found that there were 15 out of how many total outcomes again? 36. There were 36 total outcomes. This can be simplified. Okay, both of these are divisible by 3. It can be simplified to 5/12, which is approximately 42%. It's an approximation. Again, if you want to find the percentage, you take the numerator, divide it by the denominator, and multiply it by 100 because percents are out of 100. Now next, we're going to go ahead and roll. I don't have a yellow, but we'll roll the green and the red dice, and we're going to roll it 5 times. And we're going to tally up how many different times were we able to get a sum that is greater than or equal to 8. So I'm going to go ahead and make a table. Just like I had previously, like we had the previous table, I'm going to make a table that is my green and then my red. what my green lands on and what my red lands on, and what was the sum. What did my green land on? What did my red land on? And what was the sum? So let's go ahead and roll them. What did my green land on? 6. What's my red? A 3. So we have a 6 and a 3. What is the sum? 9. Okay, let's do it again. What did my green land on? What about my red? Okay, so we have a 2 and a 1. What's the sum? 3. Okay, do it again. What's my green? What's my red? What's the sum? 9. Okay, I'm going to need to make another table. Green, red, and sum. Okay. What did the green land on? What about the red? What's the sum? Good. 1 plus 2 is 3. All right, and one more time. What did the green land on? What did the red land on? 1. Okay, so we have a 2 and a 1 for a sum of 3. Okay, so now I want to identify how many of them were a sum that is greater than or equal to 8. So how many times did I get a sum that's greater than or equal to 8? 2 times, right? Right here and right here. I got it twice. So that's 2 out of how many times did I perform my experiment? 5. So 2 out of 5, which is approximately, or is, it's actually 40%. Okay, so there's our, I could have done that right down here. There's our experimental probability. We landed on a sum of 8 or higher 2 times out of 5. That's 40%. So now the question at the very, very bottom, was the experimental probability the same as our theoretical? Are they equal? No. One's 42%, one's 40%. They're not equal. Again, what did I say you need to do in order to get them close as possible? Do more trials, right? You need a large number of trials. That's important. You always want to go with the largest number of trials because a large number of trials yields or provides more accurate results. And the more trials you perform, the more accurate your results will be, more closely resembling the theoretical that your experimental will be. Yes, Jimmy? There's no such thing as too many trials. There is no such thing as too many trials. 100 trials is great, but 1,000 trials is even better. And 1,000,000 trials is even better than that. And 50 million trials is even better than that. And 10,000 million, gajillion, whatever you want to go with, trials is better than that. Okay, so that's what you're going to see again tomorrow when we do this little simulator online. For right now, you guys are going to go onto your computer. You need to log into the G Suite first, and then go to quizzes. Under your recent activity, there will be a quiz activity that's labeled theoretical and experimental block 2. Theoretical and experimental block 2.